In chapter 17, we saw how electrons that are in p orbitals can be stabilized if they're conjugated, so alternating single and double bonds. They can be stabilized if they're conjugated because the p orbitals on each of the double bonds are all parallel, including to the p orbitals on the next double bond, so that all of these p orbitals merge and they form different waves, because each p orbital is a standing wave. When the waves combine, they form bigger waves, and these bigger waves traverse the entire molecule, so that they're called molecular orbitals, with the orbital being a name for a three-dimensional standing wave that electrons are moving in. And we talked about in chapter 17 the different type energies of these possible orbitals. The lowest energy is the one that has the fewest nodes. And with every higher part of energy, you have an extra node. And a node is where you fit more wave into the same space. For example, if you pluck a guitar string, it'll go up, and then as it vibrates, it'll go down, and it'll go back up, and you don't have any nodes there. But if you pluck it harder, it'll go up and then down, up and then down, and then it'll switch and go up and then down in the other direction. So you get that one node right in the middle. And that really means you're fitting twice as much wave into the same space. You're taking that wave there and squishing it in to just 1/2 of what it was and doubling it. So you get the two. You get the wave here and the wave here, and you have that node in between. So you're fitting more wave into the same space, or more energy into the same space, and so it's higher in energy. And so the nodes always occur symmetrically, just like on a guitar string, and as you get more and more nodes, you get higher and higher in energy. So we saw these different molecular orbitals for a conjugated pi system that's not in a ring. But when you put the molecule in a ring, the waves that you form become different. Just like before, there's only one way that you can have no nodes. But now, because of the ring, there are two ways that you can have just one node in the ring. So here, just like before, you have parallel p orbitals all the way around, because all of these p orbitals, because all of those double bonds are conjugated. Whereas before, there was only one way to get a node going through the center. There's only one way to get one node. In a ring, there are two ways to get one node. You could have a node going through the bonds, and so that's like this over here, that molecular orbital there. Or you can imagine, and it doesn't matter which bond you put it through, the molecule is symmetrical, so that all of the bonds just represent one wave pattern. Or you could have them going through the atoms, and that's representing this other wave pattern here, so that you only have one node. In this case, the node goes through the atoms. So there are two ways to have one node, unlike in a linear molecule. And likewise, there are two ways to have two nodes. You could have them both through the bonds or both through the atoms. And then, so that's these two, and then even higher, you have all the nodes switching. So that's 3 nodes there. So notice, even the highest energy orbital here is relatively low on the scale of the molecular orbitals for the linear molecule. So you're fitting so when you think about the electrons you have, and in both this molecule on the left and the molecule on the right, they both have 6 electrons in p orbitals, in the p orbitals. The one on the left, you'd fill them in always from the bottom. Once you put 2 electrons into the wave, you can't fit any more in, because they're like little magnets. Once you have one going north, you can't put another one going north. Once you have one going north down, you can't put another one that way. You can pair 2 up, but if you try to fit a third, one that's already there will repel it. So it'll have to fly around in a different wave, next highest wave. So we have 2 in the bottom, then 2 in the next one, then 2 in the next one. And notice how we have 2 electrons flying in a wave that has 2 nodes. Compare that to what happens in benzene. You still have 6 electrons, 2 in the lowest, but then you can fit these other 4 in the 2 orbitals you have with just 1 node. And so they're all lower in energy. And that's the reason why benzene is so stable. And it's given the technical term in chemistry for a really stable a molecule that gets its stability from having its conjugated pi bonds in a ring is the molecule is aromatic. So that term doesn't necessarily mean a molecule smells, it means that it's really stable because of the wave patterns you get when you have conjugated pi bonds in that special ring. Now, that's nice. We have a provisional definition of what it means to be aromatic, but that doesn't happen every time you have conjugated pi systems in a ring. For example, if you had cyclobutadiene, you could have all of its p orbitals, so that would be like this molecule here. You could have all of its p orbitals in phase. You could have 2 ways that you have 1 node, either through the bonds or through the atoms, like before, so these, or you could have all of the p orbitals out of phase. That's this highest one here. Notice that we have 4 pi electrons, or 4 electrons in p orbitals. So 2 and 4. So when we fill those into these wave patterns, you put the 2 in the bottom, that's now full, and you put 1 in each of these orbitals that are the same energy. Remember, from General Chemistry 1, when you're filling orbitals, you put 1 electron in each of the orbitals before you start pairing them, because they're more stable if they're further away from each other than if they're paired, because they still push a little bit away from each other when you force them to pair up. And so here you end up with a really different scenario. You have unpaired electrons. That's extremely unstable. It's like having a magnet pointing out in space with nothing next to it. It's going to stick to the first thing it comes across, and that's any electron in any molecule nearby. So this is going to react with anything. This is going to be extremely unreactive. And so here you get something that we also never got in the molecular orbitals for linear molecules. You get unpaired electrons, and those are extremely unstable. So when you have conjugated systems in rings, because of the types of waves that you can form around the ring, you either get molecules that are really stable, those are called aromatic, or you get molecules that are really unstable because they have unpaired electrons in their moving around in the waves, and those are called anti-aromatic. So you get those 2 possibilities. Now, technically, to figure out whether something is aromatic or anti-aromatic, you would want to go through the whole process of visualizing its molecular orbitals. And you'd see, and then filling in, once you have the molecular orbitals drawn, filling in the electrons in p orbitals and seeing whether they're all paired, in which case it's really stable, or some of them are unpaired, in which case it's really unstable. That, of course, though, is a really arduous process. It takes so much thought to visualize all of that and to organize all of that information. So luckily there are a couple shortcuts. And the first shortcut, at least to drawing these molecular orbitals, is something called a Frost circle. In a Frost circle, you draw a circle, and then you take the shape of the molecule that you're dealing with, so in this case, a hexagon, and the crucial thing is to put one of the points of the molecule at the bottom. And then you draw the molecule in. Here's our hexagon, our benzene. Each of the points, where each of the points touch the circle, that represents a molecular orbital. So this is a really quick way of figuring out the relative energies in these molecular orbital diagrams. And notice that this diagram on the bottom gives me the same relative energies as these here. So if I were to fill that Frost circle, those molecular orbitals in with my 6 pi electrons, fill them in from the bottom to the top, there are my 6 electrons, and I get all of the electrons paired up, so I can tell that this molecule is going to be aromatic or really stable. If we drew a frost circle for cyclobutadiene, first step, draw the circle. Second step, crucial, make sure one of the points of your shape, your square, is at the bottom, and then draw in your molecule. Each place where the molecule touches the circle is representing a molecular orbital, and notice that we get the same relative energies as we saw in the molecular orbital diagram. So if we know there are 2 4-pi electrons here, we can fill those in from the bottom, 1, 2, 3, 4, and you can see the unpaired electrons. This molecule is going to be very unstable. It's going to be anti-aromatic. So that's a quick way of drawing the molecular orbitals for rings and with that have conjugated systems. There is an even shorter way, though. If you were to draw all of the molecular orbitals for a whole series of different conjugated rings, what you would notice as a pattern is that any time, what you would notice is that the ring that has just 2 pi electrons, 2 electrons in p orbitals, that's aromatic. The next ring that would be aromatic would have 6 pi electrons, like the benzene. The next ring that would be aromatic would have 10 pi electrons. The next one would have 12. Oh, I'm sorry. 14. Sorry about that. 14. You'd notice that. And so this is the pattern that you'd be looking at. And if you had to summarize that pattern with an algebraic expression, the expression is 4n plus 2. Now notice, the n here does not mean anything. It's not a physical thing. It's not represented anywhere in the molecule. It's just a way of summarizing an infinite pattern with an expression. So for example, if n is 0, then 4 times 0 is 0 plus 2, and we get our first number from what we saw in the frost circles. If n is 1, then we get 4 plus 2, we get 6, our second number, from what we saw was aromatic in the frost circles. If n is 2, then we get 8 plus 2, 10, that's our third number, and so on. So this n is just a variable that's summarizing a series that people noticed you got when you draw out these molecular orbitals for all these conjugated rings. So in other words, if you have 4n plus 2 pi electrons in p orbitals, then you're going to be aromatic. Then the ring is going to be aromatic and really stable. If you were to draw it out, you'd see that all of the electrons are paired. If you don't have 4n plus 2 electrons in p orbitals, then it's going to be anti-aromatic. It'll be really unstable. And if you were to draw the molecular orbitals out, you'd see you'd have electrons that are unpaired. So in general, when you approach a molecule, this is the thought process that you want to have. The first thing you want to ask yourself is, are there even parallel p orbitals on every atom in a ring? So far, we've seen that you have that if the pi bonds in the ring are conjugated. Now, if you don't have that, your molecule has typical stability. It's just normal. It's called non-aromatic. If you do have that, you have to ask yourself a second question. Are there one of those special numbers of electrons? Are there 4n plus 2 electrons in the p orbitals? If there are, then when you draw them into the molecular orbitals, you'll see they're all paired up and you'll get an especially stable molecule. The molecule will be aromatic. If there are not, if the number of electrons in p orbitals are not in that series, summarized by 4n plus 2, then if you draw the molecular orbitals, you would see that you'd have unpaired electrons that would make the molecule really unstable, and so it would be classified as anti-aromatic. So this is the thought process you want to go through in the next few exercises to establish whether a molecule is non-aromatic, aromatic, or anti-aromatic.